quantum information and computation, and that it is an important enlargement of the classical notions, which are called by most people in the world still today just information, but we call it classical information. And an example that I often raise to make the difference clear to non-mathematical audiences is that they say if the information that you're familiar with is like the information in a book, the kind of information that we study is like the information in a dream. You can't make a copy of it and give it to someone else, and if you try to describe it, you begin to forget what the dream is and remember only what you said about it. And from a cryptographic point of view, you can't prove what you've dreamed, and you can also lie about your dream without getting caught. So it has bearing on privacy. But I won't be talking about dreams anymore. I'll be talking about things like quantum cryptography, where parties can, by a combination of classical and quantum communication, even in the presence of eavesdropping, distill a shared secret key with the confidence that it is shared and secret, or else they will conclude there's too much eavesdropping, but at least they'll know they've failed. Now, quantum information, as you know, can be provisional, and if you say, which path did the photon take through the interferometer, this is a question which may have a meaning when the photon is in this stage of the evolution, and you could catch it in one place or the other, but after it's gone through the interferometer and interfered again, then the question is really a question that doesn't have a meaning. You should say the photon followed superposition of both paths. So that's an information you can say that exists only temporarily. And then after the photon has passed through, the question of which path it followed doesn't have an answer. Well, this is the largest interferometer experiment that I know of. This was done in Chicago at Loyola University. And these are a couple of the authors. And they found that there was no case in which the part of a car was observed going through one side or the other. So they commented on this. It says they didn't interview the drivers afterwards, but if they had, we know from the no cloning principle that the driver would not remember which exit he would use. Well, let's try to get a little bit more serious for a while. If I have some entanglement between Alice and Bob, I can convert it into a bit of shared secret key. So this connection between entanglement and secrecy, the entanglement may be regarded as potential for shared secret key. And the way you do that is Alice and Bob, who start off entangled here, will make a local measurement and record the result, and the measurement really amounts to an entanglement with a local environment. However, this idea of getting a shared secret key, if you think about it in the quantum way, you should be very careful that Alice and Bob keep their adversary away from their local environments. And the adversary is going to try to encroach on those environments and more aggressively. And then eventually, if the adversary can measure the environment, then the bit is no longer secret. So this is the difference between in principle secrecy and in practice secrecy. If I have a laboratory within which I've made a measurement and recorded the result, you can argue that in principle it becomes not secret, not private, pretty soon after I've made the measurement, if it's a macroscopic event. Well, I'll go back in a moment later. Conversely, you can say that standard protocols for generating quantum key that don't use entangled states can be, if you carry them out coherently with the help of local environments, they can become protocols for sharing entanglement. And then rather more complicated situations have been studied recently. You can have a non-distillable mixed state. That is a state that is entangled, but a bound entangled. It is a state from which you cannot distill any pure entanglement. But you cannot make it without having entanglement. And this sort of state is, as I said, is not useful for making entanglement, but it can be used to make shared secret key. And it involves, again, local reference systems in which you perform a measurement on this state, and you're careful to keep this local reference system away from the environment. Well, as I said, though, the problem is when you make something macroscopic, it's a little hard to be sure that it hasn't leaked out into the environment. And of course, the famous example of this is the Schrödinger cat experiment. So, if you listen carefully, you'll see here we have this. You can tell the cat is still alive, even though you haven't opened the box. So the key then is no longer perfectly secure. He might in principle learn it by doing some extremely difficult measurement on the surroundings of the labs. So this is a little interlude. I'm getting less serious. It's always good to have a test for the existence of God. Well, this is not really a test for the existence of God. That's a hard thing to do. But this is a test for the truthfulness of someone who comes to you and tells you that they, suppose someone, say Eve, comes to Alice about and says, maybe if she can, at least in the sense of the omnipotence of God. I believe the Pope recently said that God is love, and this is an aspect. But in terms of when scientists talk about God, which isn't very often, they usually are speaking of so if Eve can repeatedly pass the following test, then Alice and Bob locally generate a random qubit and ask God to pick what Bell state they have, and if God always gets the answer right, then that suggests that he has complete control or complete understanding of their environment. Well, getting back to a little bit more serious, we see that there are really three levels of privacy. We have the quantum level of like the which path information in the interferometer that only exists temporarily. And then we have this information like to be recovered in principle, but not available technology. Now, this humans can lie about it, erase it, but maybe we'll feel guilty about it. So this is a little bit different. If you lie about which particle took in an interferometer, you shouldn't feel guilty about it. It's not really a lie. And then public information, where it's very often people in government try to lie to your nose, and they outline of one of the ways of describing how information is taken, and it's by an environment in some way are made, and when the information is just one part of it, you get the information about the system. This is called classical information. Directions of quantum garbage. If you treat the environment in some other basis on the away from the realm of quantum physics and into the realm of perhaps you might say or social science, has greatly increased the scope of public information and made it hard to retract. And an example that I experienced was during the rather famous criminal a number of years ago, which occurred just about the time that the World Wide Web was taken off, I think around 1995. And there was a website devoted to up to the second news of this trial of O.J. Simpson. And we didn't have any radios or television in the IBM lab when I was working on this. So we were all watching it on our computer screens. This thing popped up on my screen. And then my colleague, John Smolin, was sitting at the next terminal next to him. somebody had pressed the wrong button, and it gone out through thousands of people had looked at it in a few seconds with the wrong information. And now this is a famous example, one of those famous examples of erroneous news that was quickly retracted, but was not before it became public. So we have, in a way, in the political arena, a trade-off between publicity and privacy, and we have, because of digital technology, we have a problem, and you may say also an opportunity. We have very cheap and easy to use video equipment, and very cheap data storage, which means that it's very easy to record everything that happens in the public or even private forever, and this can lead to a loss of privacy and also the danger of political repression. And when the most recent conspicuous example of that in the United States was J. Edgar Hoover, but I think we're coming up with more recent people who have the idea of eavesdropping on everybody, probably not for their own good. On the other hand, these recordings are sometimes good and act as a promoter of human rights and the rule of law. In fact, there's a site, or there was years ago, called thewitness.org, whose purpose was not a website only, but a move to arm people with video cameras and teach them how to use them in order to record various uses around the world.
Very accurate.
It is very accurate. I'm glad to hear that. So in the United States, a fair number of people, not including myself, and probably not including Neil, thinks that it's a good idea for society for everybody to have the right to carry a gun. But a better idea would be to have a camera. So I never go anywhere with my camera. And this is actually I'm going to be wearing it for my lecture, just in case in the audience does something that be a public policy that encourages the amateurs to make these recordings, but to restrict how the recordings can be used. And that's, of course, a very complicated question of law and social policy, which is not very well developed in most countries. Just the other day, yesterday, I slightly wrong, but this was an advertisement billboard, CNN, and their video footage, not so much for exposing corruption. Their slogan is, every citizen a photojournalist. So it's tempting to believe that once information has become, that's a, until recently, but I'll tell you why I don't think it's quite, but I want to and I'll take this thing off, it's kind of several technology. The modern world, the ancient world, and is full of examples of lost literature. One of the most of a new poem, Sappho, of Lesbos. And apparently she was very well known, and a lot of her poems were printed in many copies. Well, they weren't printed, they were copied by hand. But hardly anything remains now, and last year they found another one. And I asked some among my friends for some examples in India, and there apparently was the philosophy of Carvaka. Who knows here about that? Anyone here? Yeah, well, where this was and my informant here informed me that it was a rather materialist and even atheist philosophy, and for that reason was opposed by Hindus and Buddhists, and it was so successfully opposed that nothing remains of it now except their criticisms of it. Where they about it because it's mentioned in some other work. Well, now in today's world, there's a lot of macroscopic, publicly accessible information that is lost because no person nor any naturalist happens to record it in a stable medium. Now, about about 40 years ago, I was in Las Vegas, and I saw this pattern of raindrops on the mud in a riverbed. And a few days later, it got washed away. Now, I think if nobody had photographed it, would there be still in the universe a record of that, or would there be in the world a record of that? That's clearly macroscopic information. If any people could have looked at it and taken the same picture at the same time, it wouldn't have disturbed this. Well, here's another more recent example. Probably none of you recognize this, but this is a particular pattern of waves in the wake of a boat that was Nova Scotia, this island last summer. And here's another pattern from about that same part of the world. This is actually a rather well-documented organism here. He's got school records and bird certificates on like this, but all these birds are much less well documented. So the question is this kind of macroscopic information lost, or does it just become diffusely and spread out so as to be irrecoverable in practice? Just as you say, when you burn a book and its contents are still recoverable from the state of the smoke and ash, you should also say the heat, photons that come out from burning. So, could it be that every major past phenomenon is actually there, even if we cannot recover it? And one reason I was so tempted to believe this is that to believe the opposite is coming close to this deconstruction that regards history as not what actually happened. In fact, they deny the meaning of this word, but rather what we believe to have happened. So I was really strongly tempted to hope that this was all recorded there somewhere. But then I made some calculations. And I think now that it's more accurate to say that some information is lost, not from the universe, but from the planet. And the reason is really a kind of, you could call it bounded storage cryptography or bounded storage problem. That is that the Earth has a memory capacity not sufficient to record all of this stuff that happened on it, like the waves and the patterns of raindrops, and therefore some of it must be lost just by accounting argument. So here's an estimate of the export rate of entropy from the and that's maybe off by one of the magnitude, but around 10 to the 30 bits per year. And then, well, what about the storage of information? Well, that's again, you have to guesstimate it, but the biggest repository of information is in the igneous and sedimentary rocks. And they will store information at the density of roughly 1 bit per cubic nanometer in a classical recoverable form. And that will give us around 10 to the 22nd bits per square meter per year. So there's a gap in between those two. And just for comparison, let's look at the human information capture rate in digital media, compact discs. And this, of course, you take the population of the world and multiply it by the fraction who are heavy computer users, and take a lot of pictures that we're going to try to do, and the actual number of tens of gigabytes of such data that you produce in a year, and get something like that. Well, that looks like a fairly significant number, except that when you realize that that's for the whole world. So in other words, each square meter of the Earth is storing geologically 10 times as much information as all people are recording about their grandchildren. So here's the sort of the picture of the geological model. The idea is that we're forming new rock, mid-ocean ridges, and then so solid material that's stable for quite a while at an atomic scale gets produced here, and then it lasts for until it. And that I was certainly one of the major information storage processes on Earth. Well, the problem is that this thermal radiation going out is argued is more than this storage rate, and so the information is still in the universe, but you would have to travel faster than light to catch up with it, and so that is inaccessible to humans. So this is captured in the Yorker cartoon. So we now have a new privacy. We have the quantum level, the classical information in principle, and then, of course, the public level, and then we have this classical but escaped. It's in the universe, but not really recoverable in the world. And I guess we don't need to feel guilty about it, or it's really impossible to sincerely feel guilty about it.
Well, that assumes it doesn't. Yeah.
Well, that's right, because then you get on to my next slide here. Oh, well, let's see. This is my next slide. Maybe you should say what you mean.
You're assuming once it's gone, it doesn't interact. Astronomers are fully employed looking at interactions beyond the Earth.
Oh yeah, yes. I'll get to that in a moment. It's not my next slide, so it's one right after that. So we can't. It's not true that everything that happens out there on a classical macroscopic scale is recorded. But if we want to save something of our own choosing, how do you make it last a long time? Well, of course, why would you want to? You would want to preserve important works of literature, and you would want to preserve evidence of crimes, and very often you want to preserve it in a rather clandestine way. If it's not safe now to publicize the crime, you might want to publicize it later. But if you wanted to do either of these things, the way would be to record it in a durable digital medium and to bury many copies of it in geological stable rock formations as if it were their waste. And then you pretty much guarantee that it would survive for many years. Suppose you make companies that would have the job of doing that, of this sort of time capsule. Now, I'm going to say, though, a little remark about these entropy calculations. I was estimating the entropy production of the Earth from the thermal radiation, and that is, of course, appears to entropy the input to the Earth from the sun, because each photon coming in the visible gets split into about 15 infrared photons that go out in all directions. So it looks like the outgoing radiation has more entropy than the incoming radiation. But yet the Earth should be in entropy balance, roughly. So I think it would be more fair to say that the outgoing radiation is its apparent thermal spectrum. And in order to sharpen that contrast, imagine that you replace the sun by a laser of the same. So we're illuminating the Earth with a pure coherent state that has the same energy content as the sunlight that we get, but no entropy. And then what we have to say is that the Earth, once in a steady state, is really exporting no in its thermal radiation. In other words, it's working like a down conversion crystal, producing a lot of output, but the output is entirely tangled. But unlike an ordinary down converter, the correlations should be pretty much unobservable because they're so computationally complex. Now getting back to Neil's question. Strictly speaking, to say this is inaccessible is not right. Certainly there are things out there that it might reflect off of. It might reflect off the moon. In fact, someone else pointed out that the refractive index of interstellar space is slightly greater than 1, so if you chase it fast enough, you can catch up with it. But it's certainly very difficult to catch up with it. So I would say that serious research needs to be done to quantify this information flows, and especially to learn what determines point of macroscopic information. And of course, I would like you to pick. So, how am I doing for time?
1 minute.
I'm
Pretty fast.
What?
Yeah, pretty fast.
I'm pretty fast. Okay. Well, actually, this was maybe I should ask for questions about this because I've got another things to make a few remarks about, which I caught because of the questions that. So let's
Have you thought about the reconstruction algorithm? Let's say you erase the riverbed just so something like cow. Have you thought about the reconstruction algorithm?
No, other than just to be pretty sure it was very, very hard.
Does this or doesn't do it?
Well,
Do you refuse to have an opinion?
I would like to think that since there's nowhere else for it to go, it probably doesn't lose information.
How about black hole? I mean, that absorbs
Well, you're
information.
getting into which my prejudice is to believe that that the black holes do not destroy information, that it comes out later. So then it goes out. In other words, if the Earth stopped radiating, it would warm up pretty fast from the sun. It's roughly an energy balance, and yeah. I mean, I think maybe we're doing some things in the biosphere that look pretty irreversible, but other things that are going on for the bulk of the Earth and the atmosphere are about the same now as they were years ago. The average rock doesn't have higher or lower entropy than the average part of the atmosphere. The biosphere is a very small part of it.
There could be different types of information in the same physical object.
Yes.
You might be losing one, but then it depends what is relevant for you versus what is relevant for someone else.
Yes, well, I was trying to not take a position in terms of the value of the information, but just quantify it entirely by entropy.
What's a rough idea of how you calculate number of bits of information per square nanometer or something? Like how do you calculate information density from a volume or?
Oh, like in the rocks? Well, I just said that you might say that was a lower bound, because when you have a solid rock and it doesn't get too hot, there isn't much diffusion of the atoms. So the atom, which atom is in which place, is stable over geological time frame. Things like vibrations and hydrogen bonds and so on are not stable. So I was just looking for that part of the chemical structure is stable over hundreds of millions of years. It's not stable forever. If you leave anything alone for a long enough time, it will tunnel into becoming iron by nuclear rearrangement. So there's all kinds of. Then Dyson wrote a famous paper quite a number of years ago about what processes that happen in the universe extremely slowly, but if you wait long enough, overlap.
So with global warming, will the entropy of that change?
What?
With global warming, will the entropy of that change?
Yeah, I think so, but that's I would say again small on the geological time scale. Maybe even on the scale of the atmosphere and oceans, it's a lot, but that's a very little part of the Earth.
A problem about the selection of information.
Yes.
What I mean, when the Twin Towers attack occurred, it was known that something would occur, but it was not considered because of the lot of information it was, and so it was not.
Yes.
How to select the relevant information? I mean, is there some idea to choose?
That's a whole other topic, which information theorists and statistical mechanics people try to avoid. But if you're talking about preserving historical records, then implicitly you're getting interested in that. And it may have a physical element if you say in our world, what sorts of information gets preserved? Perhaps the sorts that get preserved, that get destroyed, are the ones that are considered less important.
Some other questions?
All right, this was the question, I mean, this very small question, dissipation, computation, and thresholds for self-organization. So the question is, if you have any kind of hardware environment which is capable of computing or self-organization, there will be some trade-off between among dissipation error and computation rate. And if you make the hardware more complicated, that could reduce the error or increase the amount of computation done per unit energy dissipation. And this trade-off is largely unexplored, except by engineers, especially the three-way trade-off where you care about energy dissipation and error. Often people will study thresholds of whether it's possible or not given an infinite amount of energy. But really it's a three-way trade-off. And here's examples of engineers studying this thing. We have the process of fractional distillation, which in the limit of can be done with a cost equal to the negative free energy mixing, say water and alcohol. However, in a practical still, it doesn't work that well when chemical engineers study what the throughput is versus the design and the quality of the product compared to the ideal. We have the ultimate scaling of computing. You can't make I've often been known for arguing in behalf of Landauer's principle that computation doesn't require dissipation. But if you have computation with errors and you need to correct the errors, that is a many-to-one process, so by Landauer's principle it does dissipation. And the question is how much? And then that was just the question I alluded to above. So generally the conclusion is that you can't build a three-dimensional scalable computer, but you can probably do it in 1 or 2 dimensions. But now this is the question that immediately I was reminded of by Neil last night. So we were talking about the trade-off between dissipation and computation. Can you think of an example of dissipation without computation? That is where we waste energy and nothing with and that's, of course, there's a good example of this. Here is a system in which we have a tank of water that's heated from above and cooled from below. And so we just have a heat flowing through this with no convection. And it looks like the only kind of computation that would do would be a kind of analog solution of the heat equation. But in fact, if the water contains some impurities, it may take a long time, then something different might happen. You might have this thing like turbines and people who tend them and grow trees and trees. And the stability of this turbine civilization will be determined not by how hard it is for it to fluctuate into existence, but rather by the break even or not between the rate at which it breaks down or decays and the rate at which it can rebuild itself. So those are two kinetic features, and presumably there is a threshold for self-organization of this impure water that has to do with if it was a 10-degree temperature difference, the turbines would break down more often and the people could rebuild them, because the people would be pretty sluggish. They couldn't grow very much food, and they would be kind of lazy, and they just couldn't keep up with the natural processes of decay. Whereas if you made a greater temperature difference, the lights would shine brighter, the trees would grow faster, and the people would have more energy. So that's my contribution to that subject.